Let's go over a very, very important theorem, which is called the parallaxes theorem, which is heavily used in civil engineering and mechanical engineering. Parallaxes theorem refers to translation and is being used whenever you know the moment of inertia of an object about an axis that goes through its center of mass, and you would like to calculate the moment of inertia about any other point, or vice versa. That is, you know the moment of inertia about any point in space of a particular rigid body, and you would like to deduce the moment of inertia of the same object but about its center of mass. This is how it's being defined. I is equal to IC plus MD squared. That's it. It's very simple. What is I? I refers to the moment of inertia about any point. IC, by convention or by the way is being used, refers to the moment of inertia about the centroid or the center of mass of the object. M refers to the mass of the object, and D is the translation vector, which is the position vector connecting the center of mass point all the way up to where you want to calculate that new moment of inertia. And that's it. So let's imagine that you have a rod and that you know its moment of inertia about its center of mass. So let's say for a rod of length L, the center of mass is halfway through. And let's imagine that the rod is rotating about that axis of rotation. And you happen to know that I about the axis of rotation is 112 ml squared. But now you're interested in, say, figuring out or calculating the moment of inertia of the same rod if your axis of rotation was, say, located on one end of the rod. So let's give them some names. Let's call C the point where the center of mass is located, and let's call A the point on one end of the rod. So this is the problem. You are given the moment of inertia of that rod about point C, which refers to the center of mass, and you would like to figure out the moment of inertia about point A, which is located, let's say, at one end of the rod. So if we apply this, we need to figure out who's who. So IA, which is the one you like to figure out, must be equal to IC plus MD squared. IA is the moment of inertia about point A. IC is the moment of inertia about the center of mass. That's what we look for. And therefore we need to figure out M and D squared. M is the mass of the object. Let's assume that we know it. And D refers to the translation vector that goes from the center of mass all the way up to the point at which you want to calculate that new moment of inertia. So in your case, boom, this is D, and that's it. So in our case, D is equal to L over 2. Done, problem done. So IA is equal to 112 ml squared plus ml over 2 squared. Let's solve the algebra. We have 112 here, we have 1/4 here. Factorize ml squared on both sides. This is a 12, this is a 4, so 3 and 3. 3 and 1 is 4. 4 over 12 is 1/3. And you end up with IA is 1/3 ml squared. Voila. That's all there is to it. So it's pretty simple. All you have to remember though is that when you use, so technically I could have calculated the moment of inertia about point B right here, or point D right there, no problem, or point E. All I have to do is translate it. Now, you have to remember, so in this case, I would translate from here to here, then I would translate from here to here. Obviously, the translation vector is being squared, so it doesn't matter whether you go left or right. The key to remember when using the parallaxes theorem is the way it's being written here is you can only go from the center of mass to any other point, or from any other point to the center of mass, in which case you go like this, right? You just move the terms around. So that's the first thing. You cannot go from any point to any other point. One of those two must be the center of mass. Second, remember that this refers to a translation, which means that you are translating the axis of rotation. You cannot use the parallaxes theorem to figure out the moment of inertia about an axis, let's say going like this, because this axis is being rotated with respect to your original axis. You cannot use that for a rotation. For rotation, you have another theorem which is called the principal axis theorem. But this one is the parallel axis theorem, which refers to translating in the parallel manner your axis of rotation. So you can only translate your axis of rotation from one position to the other. You cannot rotate it. So again, if you like to figure out a rotational system, you will have to use another theorem. So keep in mind, parallaxes theorem refers to the translation and only translation of your axis of rotation from one point to the center of mass or from the center of mass to one particular point. Let's do an example. Let's use our favorite pendulum, which now is being composed of one rod of length L. Let's call it a bar, which is connected to a particular disk of radius r and of mass md, or mass md. And let's imagine that our pendulum is rotating about this point A. And I would like to figure out I, the moment of inertia of the whole system as it rotates about point A and the axis of rotation which is perpendicular to the plane. Now obviously this is a composite system. The nice thing about moment of inertia is it's additive. Therefore, the total moment of inertia is equal to the moment of inertia of the bar plus the moment of inertia of the disk. And I would specifically would like to calculate the moment of inertia of both systems about point A. So let's imagine that we only know the moment of inertia of each subsystem with respect to their center of mass. That is, we know that I of the bar about its center of mass C is equal to, I forget, I had it before, 112, sorry. 112 mass of the bar, length of the bar, L. And let's imagine that we also know that the moment of inertia of the disk about its center of mass is 1/2. Okay, so this I is the moment of inertia about an axis going through its center. And this one is about an axis going about its center of mass. But really, I want the moment of inertia about this point, not about those 2 points. So first, I will need to translate from here to here for the bar. And then for the disk, I will need to translate from here all up to here. So let's do the first translation. This one. I want the I of the bar about A. And I happen to know the I of the bar about its center of mass. So all I have to do is calculate the I of the bar about its center of mass, and I'm going to add the mass of the bar times the translation between the center of mass and the point A squared. In this case, I will call this D1. This is my D1. All right. So this is this one, 112 MBL squared plus MB, and D1 is L over 2. Hop, 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 hop. So I have a 4, I have a 12, so same as above. This is nothing than 1/3 mass of the bar, L squared. Okay? Now, similarly, I want the I, or the moment of inertia of the disk about point A. So I know I'm going to have to translate because I only know the one about its center of mass. So I need to go from the I of the disk about its center of mass plus the mass of the disk times the translation term, which will be the position vector between the center of mass of my disk all the way up to where I want to calculate the I. So this will be D2. So in this particular case, D2 is nothing else than L plus R. So I just need to plug and play. This will be 1/2 mass of the disk. No, I'm sorry. This must refer to the radius of the disk by definition. My bad. Hop, hop, hop. Plus mass of the disk. D2 is L plus R. Hop, hop, hop. Done. So what do I have? I have 1/2 mdr squared plus mdr squared. That's 3/2 mdr squared plus mdl squared. So I have md 3/2 r squared plus l squared. Therefore, my I total is just this plus this. I total is 1/3 mbl squared plus md 3/2 r squared plus l squared. So this will be my moment of inertia about my composite system about point A. And the way I did it is first I decomposed my moment of inertia into the sum of the moment of inertia of each subsystem. I started by the moment of inertia about the center of mass of each system, and then I translated each towards the point about which I want to calculate the moment of inertia using the Paraxis theorem, because between this axis rotation and this one, all I had to do is translate it by distance d1. They're both going perpendicular to the plane. Similarly, I translated this axis rotation all the way up to here by a vector d2 as I've applied the Paraxis theorem about this term, for this term.